Okay, here we are at the presentation for the power triangle. I'm going to do this in two parts. This is part one, and we're going to focus on the terminology and the concepts behind the power triangle. And then in part two, we're going to get into some of the math. So to start off, what I've created here in the upper right-hand corner is a simple AC circuit that has a purely resistive load. And the reason why I chose to start here is a purely resistive load does not resist changes in either current or voltage. Now, that statement may be a little confusing. I think it'll make a little more sense once we look at inductive loads and capacitive loads. But the best way to actually show that is here on the graph. So what I have so far on my graph is voltage, and I have plotted my voltage with a peak of 1 volt in this direction and negative 1 volt in that direction. And the reason I picked those magnitudes will become apparent in just a minute. But if I plot the current that is in this circuit, it would look something like this, and I have a peak of 1/2 volt and a peak of a negative 1/2 volt in the opposite direction. But these waveforms are what we call in phase. And what we mean by in phase is they are leaving the zero together. They are coming back together at 180 degrees, and they come back together again at 360 degrees. Or in other words, their periods are the same. So the cycle begins and ends at the same point. That is the definition for those being in phase. And where that is a benefit is when I actually calculate the power for this circuit. Now, the way I'm going to calculate power is something that we're similar to just from our Ohm's wheel. I'm going to multiply my voltage times my current. And I'm going to graph that waveform here. So this is my voltage times my current, but if you notice up here in the legend, I'm calling it volt amperes. Okay? That's going to lead us to one of the terms we're going to learn in our power triangle. But before we get to that, I just want to look at the waveform itself. The waveform starts at 0. It goes to a positive magnitude and comes back to 0 and then goes positive again. As you remember, if we take two negative numbers and we multiply them together, we get a positive. So this waveform is only going to be in the positive direction. And it is completely at or greater than 0, which is a good thing. That means that we're using all of the power. And again, we're going to get into that in just a minute. But that is a purely resistive circuit. Let's add some inductance into our circuit. So here in the upper right-hand corner, I still have some resistance in the circuit, and I have my inductor that I have added in here. Okay? I have my same waveform, magnitude of 1 in each direction, and I am going to plot the current for this, but we have an issue. In inductive loads, they resist changes in current. And in an alternating current circuit, we're ever changing the voltage and the current. And we've just placed something in that circuit that is going to resist the changes in the current. And why is that? Let's look at this little animation that I've created. If I have a wire, this is just a cutaway of a wire, and I'm showing a minus sign there, so that means that my current is going into the screen. Now, if you recall from our lesson on magnetism, we can use the right-hand grip rule, and you point your thumb in the direction of conventional current flow, so that would be into the screens, and we're using our right hand. You're pointing your thumb into the screen. Your fingers, if you can imagine them wrapping around the conductor, are going to be rotating in a clockwise fashion, and that's why my animation is showing the rotation of a clockwise fashion. Now these are two conductors of many, many conductors that are inside this inductor, but I'm just showing two here just for clarity. So as I have current flowing into the screen here in this conductor, it is creating this magnetic field, and that magnetic field is cutting this conductor here to the right. Now, the magnetic field is actually expanding from the viewpoint that we're looking at is from left to right. But that would be the same as the conductor moving into a static magnetic field from right to left. So now we can use our Fleming's right-hand rule, and if we point our right thumb in the direction of the conductor moving, which would be from right to left like we just described, and you point your first finger in the direction of the magnetic field lines are going, so that means my first finger would be pointed down or towards the bottom of the screen. So with my thumb pointed from right to left and my first finger pointed down, where is my second finger going to be pointed? It's going to be pointed out of the screen. And that's why I have a blinking negative sign and then plus sign, because the negative sign is my AC source has current flowing in that direction, but my magnetic field lines that are cutting that conductor that is adjacent to other conductors is going to induce a positive current, and that is what is called reactance. And because of that, we have a phenomenon that happens in inductive loads. And we have a three-letter acronym to help us remember what leads what as far as voltage and current. And the three-letter acronym is called ELI. So the L, as you recall, is the letter that represents inductance. So in an inductive circuit, we have our voltage, the E, leads our current, I. E comes before I in the three-letter acronym ELI. Voltage leads current, and voltage leads current in this circuit because we are inductive in nature. So now I'm going to plot the current, and I need to plot it with what we call a phase shift, because the current is not going to be in phase anymore with our voltage. It is going to be lagging my voltage. Remember ELI, the voltage leads the current, or the current lags that voltage. So in this case, the data that I used to generate this waveform, this is a 36-degree shift. So if you look at this, that's a 30, 60, 90. We're right at 36 there. So we are no longer in phase. They're not leaving zero together, they're not coming together at 180, and they're not coming together at 360. There is a phase shift, so they are out of phase by 36 degrees. Okay? Now I am going to plot my voltamperes. And this is showing an issue, and I hope you can see the issue on the screen. We have a positive voltage up here to 36 degrees, but we have a negative current up to 36 degrees. So my voltamperes for that first 36 degrees is negative, and that is undesirable. Also over here, my voltage goes to 0 at 180, but my current is still positive. So my voltage starts to go negative between 180 and 36 degrees past 180. And my current, it takes that long, it takes another 36 degrees for it to actually go negative for me to get a product of a positive number. So I have a negative voltamperes there as well. And so now we're going to learn another term, and that is reactive power. Reactive power is power that is not usable to us. Reactive power is what happens when we have wasted current. This is current that is used to fight itself inside this conductor. We showed that the current flow in a conductor was creating a magnetic field that was fighting against itself. That is that wasted current that we're seeing here, which causes this phase shift. Let's look at the power triangle and how this applies. So on the bottom of the screen, I have a triangle that I've put here, and it has obviously 3 sides. And on one side, I'm going to call active power. On another side, I'm going to call apparent power. And on the third side, I'm going to call reactive power. And we already kind of have an idea of what reactive power is. Now, those are long terms, and in formulas, we're actually going to simplify these with letters. So for active power, we are going to have represent that with the letter P. For apparent power, we're going to represent that with the letter S. And for reactive power, we're going to represent that for the letter Q. And for us to keep these separate, because they are different types of measurement, we have different units. So for active power is watts. And if it's large enough, we use kilowatts or kW. For apparent power, we use volt amperes. Okay, we already kind of established that up here. We have something called volt amperes up here. And for reactive power, we have a term called volt amperes reactive, or VARs. And if it's large enough, it's kVAR. So the angle at which this slope happens is called the power factor angle. Now let's look at power factor, and you may have seen this on motors. The power factor is a unitless measurement that is a ratio, and it is a ratio of my active power over my apparent power. Or if I take my watts and I divide it by my volt amperes, I will get a power factor for that particular circuit. So let's just take this circuit as an example here, and let's say that my power is 8 watts. My active power is going to be everything that is above the x-axis here, okay? And I'm saying that that is 8 watts. My volt amperes, my apparent power, is this whole graph here, okay? That whole line I'm saying is 10 volt amperes. So if I want to get my power factor, I just take my 8 and I divide it by my 10, and I get a power factor of 0.8, which on my graph here I'm showing that the power factor is basically this ratio here on the height of this reactive power line. So the power factor of 1 would be a pure power system. We're using all of the power that we're producing. But here at 0.8, we're not using all of the power. Some of the power is consumed within the inherent parts of the system itself. And the steeper this angle, the less desirable it is. So a power factor of 0.5 would be a very inefficient circuit. A power factor of 0.9 would be something that is very efficient. Okay, so I've come back to our purely resistive load, and I want us to understand power factor a little bit better. So we have our power factor here, and in my purely resistive load, here is my volt amps. And remember, it was all positive. So my power, because there is no reactive power, it's all above the line, I have 10 watts of power. Well, my volt amperes are 10, so my power factor would be 10 divided by 10, which is 1, and I would in effect have this. I would have my apparent power and my active power would be on top of each other, and that would give us a power factor of 1. Okay, I'm hoping that is starting to solidify in your mind a little bit. Now that's one type of issue that we have with alternating current circuits. Let's look at when we have a capacitive load. Okay, now we're going to look at a capacitive load. So I have changed my circuit here where I have some resistance and capacitance in my circuit with my AC source. Still have my same sine wave. Now a capacitive load differs from an inductive load in that it resists changes in voltage. If you recall from our earlier lesson on capacitance, a capacitor is much like a battery in the circuit where it gets charged up and then can discharge into the circuit. So as we are approaching here 1 volt, we're charging up this capacitor. Well, as soon as we start to decrease our voltage, this capacitor is going to fight that decrease in voltage by discharging into the circuit, and that is going to cause a phase shift in our current in this circuit, but it's going to be a phase shift in a different direction. We have a 3-letter acronym that we can use to understand that relationship. So ICE is our 3-letter acronym. The C stands for capacitance. The I stands for current, and the E stands for voltage. And in a capacitive load, our current, our I, is going to lead our voltage, E. Or another way of thinking it is our voltage is going to lag our current. Either way is correct. So let's plot, with knowing this, let's plot the current up here on the graph. So now, with the same voltage waveform, I now have a current waveform that is leading that voltage waveform. So here I have current that is already above 0. They're not passing through 0 together. They're not passing through 180, and they're not passing through 360 together, so they are out of phase. And I have done a 36-degree phase shift, but in this case I had to do a phase shift in the opposite direction. The current is leading the voltage here by 36 degrees. So now let's look at our volt-ampere waveform and see what problems this is going to cause for us. Okay, so here we have both a positive current and a positive voltage, so we start off in a positive direction. But since the current is leading the voltage and it passes through the x-axis while the voltage is still above the x-axis, it's going to create this negative dip in my volt-ampere waveform, which is going to create some reactive power. And then when they're both negative, it's going to go positive again. And it's back to the point where the amperage goes positive, but my voltage is still negative, that I have my negative volt-ampere waveform, which is some more reactive power that I have in the circuit. So to identify our reactive powers, it is there and there. And that is not what we want in a circuit, because that is wasted energy, and we have wasted current that is fighting against either the charge or the discharge of that capacitor. Let's look at how this has affected our power triangle. Now I turned the power triangle upside down because this is actually a phase shift in the opposite direction, and that's a very important concept for us to understand. A capacitive shift is in the opposite direction from an inductive shift. I still have my active power, my apparent power, and my reactive power, and they are still within the same units, and I can calculate a power factor by taking the ratio of my active power over my apparent power. Now a capacitive load is rare in the field. Why? Because inductive loads are much more common. Motors are inductive loads. Transformers are inductive loads. And we don't typically have devices in the field that are capacitive in nature to overcome that. So the loads that we're going to see are going to be more inductive than capacitive, but we're studying this because it's important to understand the concept, and we're going to talk about the reason why now. So on the screen now I have a graph that is showing both my capacitive and my inductive phase shifts here. Okay, colors are the same. This would be a active power, that would be apparent power, and this would be my reactive power. They're just in different directions. So if my purely resistive load is just right down the middle here, my inductive load is obviously up here because my phase shift is going to be in this direction. My capacitive load is down here. So I said that in the field we have more inductive loads present. It's just inherent because of motors and transformers and other devices that create that inductance in the circuits. What could we do to bring it closer to this purely resistive load, an inductive load? Think about that just for a minute. What if we combined this and this circuit together? So we have inductance in there, and we have resistance, and we intentionally added capacitance in there. That would be fighting this phase shift in this direction, because the sum of these two, if they were exactly equal, would be the equivalent to a purely resistive load. Now, I said that our inductive loads are things like motors and transformers. Well, the inductance, motors are not always running, they're going on and off. It would be rather impossible to always be adjusting this capacitive side to get to a purely resistive load, but we can bring an inductive load closer to the mark of a purely resistive load with adding capacitance into the load. So that is why it's very important to understand the relationship of the power triangle and phase shifts, and how we can use a phase shift in one direction to counteract the benefits or the drawbacks of a phase shift in the other direction. So that is the end of part 1. So in part 2 we're going to look at some of the mathematics behind this. Because these are triangles, we're able to use Pythagorean's theorem, and we're able to use trigonometry, the sine, cosine, and tangent, to do some mathematical operations on this. But we'll get into that in part 2. So look for that lesson soon. We'll see you then.